Everyone, Mr. Neighbor here, and we're going to talk about gravity today. So gravity is probably most evident when you're in free fall. When you're standing on the earth, it doesn't really seem like much, but gravity is most visible to us when we're in free fall because gravity is a type of an acceleration. Gravity means that every second you're going to change 9.81 meters per second. So in 2 seconds time, you're going to be traveling almost 20 meters per second. And you're going to continue to get faster until the air resistance, the upward force, actually meets and increases to the point where it matches the gravitational force. And that is when you reach terminal velocity. If you spread out, kind of like a flying squirrel as you're going down, after going down straight, the force of your air resistance will spike again and it will slow you down. And then eventually that spike in the air resistance will come down and it will come down to match the force of gravity. So that would be a dynamic equilibrium, if you want to call it like that, where the two forces are equal, but you are actually moving, you are dynamic. So remember terminal velocity. It's when you reach the fastest you possibly can because your forces are finally balanced. The gravitational force is being canceled by the free fall, the air resistance force. All right, so some practice. I'm losing my voice. A 1 kilogram book and a 2 kilogram book are both held 1 meter above the surface of the moon, where there is no air friction. That's because there's no air. Which of the following is true? When released, the objects won't fall because there is no gravity on the moon. When released, the brick will land first. When released, the brick will land first because a greater force is pulling on it. When released, the brick will land at the same time as the book because the force of gravity is the same on both of them. When released, the book will land first, or none of the above. Think about what free fall is. It's just what gravity is for that planet or moon or whatever. So even though we're talking about the moon, let's just think about it accelerating on Earth at 10 meters per second squared. So after 1 second, this object is going to be going 10 meters per second. But so is this object. In 2 seconds, this object's going to be going 20 meters per second. And so is this one. The only thing that's going to slow these down is some upward friction force, which is not present on the moon because there is no air. And because of that, when released, the brick will land at the same time because the gravity is the same on both of them. The force is not the same, but the acceleration, gravity, is the same on both of them. If you want to think about it as space-time is warped the same by the pull of the moon for both of them. So they're going along the same geodesic, but it's going to land at the same time. If you put two objects in a vacuum, a feather and a hammer, if you put them in a vacuum and drop them, they're going to land at the same time. It seems bizarre, but there's videos out there to show you that. I think Mythbusters does a video on that, so you can look that up. All right, projectile motion. Projectiles are any object with both vertical and horizontal components creating an arced path or trajectory. So if I kind of lay out some baseballs here, this might be a trajectory of a baseball if you throw it, this kind of parabola shape. It has vertical components to the velocity and horizontal. So whenever you throw that ball, it has a horizontal component. It's traveling through the air. That speed is not changing because we're going to neglect air resistance. So these balls at the bottom here should probably be further to the right. But notice all of the green arrows are the same length. However, the vertical velocity is eventually going to come to a halt, and it's not going to be there. At this point, at the apex, there will be no vertical velocity because it's going to transition. It's going to start transitioning into the downward velocity. And when you add these two vectors together and get a resultant, so putting this vector over here and then going from tip to tail, you get a blue vector here. And that shows the direction that that object is moving. So here you're going to see it again, again. And then here, the blue vector is the green vector. And now it's going downward, downward, steeper downward, and even steeper yet downward. So these are just a visualization of the velocities that are present on a projectile in motion. These are velocities, not force vectors. If we were talking about forces, there would only be one, and it would be the same everywhere, and it would be the force due to gravity, okay? But when you break it down into its velocity, you're going to see a vertical component like we did in red and a horizontal component like we did in green. All right, the law of universal gravitation. This is a formula that is used to calculate the force of gravity between any two objects having mass. So F stands for the force of gravity. Big G is a universal gravitation constant. It has a very complex label. I didn't write it though. And it just makes all this kind of cancel out to be newtons in the end because we're talking about a force. M1 and M2 are masses of your two objects, and D is the distance between the center of each object. So I want you to think about the mass of the Earth. All right, some practice. Two spherical objects have masses of 200 kilograms and 500 kilograms. Their centers are separated by a distance of 25 meters. Find the gravitational attraction between them. So I'm just going to take my formula and plug in what I need. So F equals G. I'm not going to write out that number, but that's what G is equal to. I'm going to multiply that by 200 and then multiply that by 500. And then I'm going to divide that by 25 and make sure my 25 is squared. I would recommend typing this number in, storing it in the letter G for future purposes. So then you can just type the letter G as well. All right, when I do that, I get out approximately 1 times 10 to the negative 8 newtons with sig figs. So less than a newton worth of force. These two objects are probably about what some of you might weigh. I'm around the 780 kilogram, or sorry, that's false. I'm around the 78 kilogram range, so around 780 Newton range. So this might be twice some of your sizes roughly, depending if you're a senior maybe. But anyway, so not very much force, okay? These objects are much bigger though, and we're gonna see a bigger force maybe from them, but the distance also matters. So let's look at this. So we use the same equation, G, plug in my scientific notation numbers. And when I plug in everything, I will get out this for my force, 1.4 times 10 to the negative 9th newtons, which still smaller than a newton. Not very much force, probably because the distance increased. And notice how big of an impact the distance has. This number, this force, is even smaller than the force we calculated with these smaller objects. The force is so impactful by the distance because that distance is squared, and that squared makes a huge impact. And also gravitational force, it's probably one of the weakest forces out there. Electric force, magnetic force, a lot stronger.